Welcome back to the deep dive. Today, we are focusing on something foundational, something, often overlooked, but entirely indispensable to modern infrastructure and construction. We are putting the humble yet highly critical stainless steel fastener under the metallurgical microscope.
It's so true. Fasteners are indeed the unseen heroes of the built world. I mean, think about it. They are the primary load-bearing connectors holding together everything from, say, the intricate machinery in a clean room to the immense structural joints of skyscrapers, bridges, even delicate surgical implants. Their reliability is not just an engineering preference. It is, well, it's the cornerstone of system longevity, structural integrity, and public safety.
Exactly. And our listener wants a comprehensive, deep analysis of stainless steel screws. What they are, why we use them over the extremely common carbon steel alternative, and crucially, how an engineer or even a knowledgeable DIYer chooses between the three most prevalent stainless steel grades, 304, 316, and 410. We need to explain not just the what, but the why of the chemistry, because the stakes are far higher than just avoiding a rusty screwhead. Choosing the wrong material can lead to, well, accelerated corrosion, immense financial loss, or, worst case, catastrophic structural failure.
That is the precise mission for this deep dive. We're going to start by analyzing the fundamental mechanism that allows stainless steel to resist rust, that self-healing passive layer we hear about. Then we will spend significant time comparing the three major grades, 304, which is also called A2, 316, or A4, and 410, or C1. We will break down their specific chemical composition, their unique crystal structures, of the resulting mechanical properties, and finally weigh their price against the total cost of ownership in demanding environments.
Okay, so let's unpack this by starting with the fundamental problem that stainless steel was invented to solve: corrosion. We invest massive amounts of energy to extract iron, turn it into strong steel, but nature is always trying to take it back. Corrosion is an inevitable electrochemical process, a slow, relentless return of strong metal back to its original, weak state of iron oxide, which we all know as rust. It is literally entropy at work, trying to reclaim the refined material.
That is an excellent way to frame it, as the metal's slow thermodynamic journey home. When we discuss ordinary carbon steel, its failure is primarily due to this corrosion process, and it initiates instantly when oxygen and moisture reach the bare iron surface. The oxide film that forms on standard carbon steel is it's porous, it's flaky, and non-adherent, meaning it cracks and falls off, constantly exposing fresh, vulnerable steel underneath the elements.
And that's where the century-old breakthrough of stainless steel comes in. It's not just a slightly better steel, is it? It's a completely different category.
It is. The core solution was to create an alloy of steel with a significant minimum amount of chromium, or K, typically 10.5% or more, and often nickel. This blend provides inherent resistance to rust, a defense mechanism that permeates the entire structure of the fastener, which is a sharp contrast with the protection offered by, say, a thin surface coating.
So stainless steel has a fundamental internal defense system, and that system relies entirely on the presence of chromium. Can you walk us through the actual physics and chemistry of the secret mechanism behind this resistance?
Of course. The secret lies in a fascinating phenomenon called passivity. As soon as the stainless steel surface, specifically the chromium component, is exposed to air or water containing oxygen, the chromium atoms spontaneously react to form an ultra-thin, highly stable, tightly adherent layer of chromium oxide on the surface.
How thin are we talking about here? I mean, is it something you can see or feel?
No, not at all. We are talking about a molecular level shield, often only 1 to 3 nanometers thick. To put that in perspective, that's thinner than a strand of your DNA. Yet this layer is incredibly dense and non-porous. It acts as an impenetrable physical barrier that prevents further reaction between the underlying iron content in the alloy and the corrosive environment, like moisture or chemicals. We call this layer the passive film.
Wait, if the passive film is only a few atoms thick, how can that possibly withstand the mechanical forces, the high pressures, the sheer environmental stresses of being a load-bearing fastener? Surely it must be scratched or damaged eventually.
And that is where the key advantage, and really the true genius of stainless steel lies. The film is dynamic and self-healing. If that passive surface layer is mechanically scratched or abraded or chemically damaged, the fresh, unoxidized chromium beneath the damage is instantly exposed to oxygen. And if sufficient oxygen is available, the passive chromium oxide layer naturally reforms almost instantaneously, regenerating the protective shield.
That is the crucial difference then. It's not just resistance, it's active self-repair. As long as oxygen is present, which it is in almost every atmosphere, the protection maintains itself indefinitely.
Precisely. This inherent self-healing capability is why stainless steel is mandatory for long-term critical applications. It guarantees that unlike, say, a zinc coating, which fails irreversibly once its thin layer is penetrated, stainless steel protection is intrinsic and persistent.
That brings us to the topic of passivation. Now, if the chromium oxide layer forms naturally, why do engineers often specify an additional chemical treatment? It seems a bit redundant.
That's a great question. Passivation is an enhancement step. It's a way to absolutely maximize that natural layer's effectiveness before the fastener ever enters service. It's a chemical bath, usually involving a mild acid like nitric acid, or increasingly for safety and environmental reasons, citric acid. The purpose is twofold and highly meticulous.
Okay, what's the first purpose?
First, it is about deep cleaning. During the manufacturing of the screw, the cutting, the threading, the cold-forming microscopic particles of free iron from the tooling or handling equipment can become physically embedded in the stainless steel surface. These iron particles are not stainless steel, and they will immediately rust upon exposure to moisture, initiating corrosion right on the surface of your expensive stainless fastener.
Ah, so the acid essentially cleans the slate. It dissolves only those contaminants and leaves the pure chromium-rich alloy behind.
Exactly. The acid dissolves those contaminants along with any low protective oxide scales that might have formed during heat treatment. Once the fastener is rinsed and dried, this freshly clean, uniform chromium-rich surface spontaneously reforms an optimized passive layer upon immediate exposure to oxygen.
And this professional treatment results in a measurable performance increase. I mean, is it really worth the extra step?
Oh, absolutely measurable. A properly passivated 304 or 316 stainless steel fastener can exhibit corrosion resistance that is an astounding 5 to 20 times better than an untreated one. This is why passivation is mandatory for applications where pristine corrosion resistance is critical. Think food processing equipment, pharmaceutical manufacturing, and medical or surgical implants, where chemical inertness is paramount. It's really the highest standard of surface preparation.
This inherent self-healing mechanism stands in stark contrast to the workhorses of the carbon steel world, coated fasteners, specifically those that are zinc-plated or galvanized. What is the practical difference in protection day to day?
The difference, as we established, is fundamental: inherent versus sacrificial. Stainless steel's protection is alloy-based and internal. Coated carbon steel protection is external and sacrificial.
Explain sacrificial.
Take standard electro-zinc plated steel. It's cheap, it offers a bright, visually appealing finish. But the thin coating, typically less than 0.5 mils thick, is purely for aesthetic, indoor, or very mild, short-term dry use. That thin coating is easily penetrated or scratched during installation. The moment the underlying carbon steel is exposed, the game is up.
And once the underlying steel is exposed, rust blooms almost immediately. I think we've all seen that.
It does. Now consider hot dip galvanizing, or HDG. That's a significant upgrade. The fasteners are dipped in molten zinc, creating a much thicker coating, often 1.0 to 4.0 mils thick. This thickness provides superior longevity, suitable for general outdoor construction, especially in contact with chemically active materials like pressure-treated lumber. However, even HDG is sacrificial. In the presence of an electrolyte, the zinc sacrifices its mass to protect the steel. It's a race against time. Once the zinc layer is consumed, the underlying steel begins to rust rapidly. Stainless steel never needs a sacrificial layer because its entire mass is resistant.
Okay, so stainless steel sounds like the perfect material, which usually means there must be an Achilles heel somewhere. And I think I know what it is. It's how it interacts with other non-stainless metals.
That is the critical limitation: galvanic corrosion. Stainless steel, particularly the austenitic grades like 304 and 316, is a highly noble metal, which means it sits very high on the galvanic series scale and is highly resistant to corrosion.
Okay, so what happens when you pair something noble with something less noble?
If you bring a noble metal into physical and electrical contact with a less noble or active metal like aluminum, copper, brass, or standard galvanized steel, in the presence of an electrolyte, and even simple rain is an electrolyte, you create a galvanic cell. You basically create a weak battery.
And in that battery, the stainless steel acts like a bully, right?
Exactly. The less noble metal acts as the sacrificial anode and will corrode preferentially and rapidly to protect the noble stainless steel cathode. The corrosion rate of the active metal is dramatically accelerated, often far beyond what normal environmental exposure would cause.
So, using a highly durable 316 stainless screw to attach a bracket made of standard aluminum to a boat hull, or even just outdoor aluminum siding in a wet environment, is actually signing the aluminum's death warrant. The aluminum will pit, dissolve, and fail prematurely just to keep the screw safe.
Precisely. This failure mode can be highly localized and destructive. We often see it where a beautiful stainless steel screw is perfectly fine, but the galvanized washer or the aluminum substrate surrounding it is dissolving into white or red powder. This is why material compatibility is just as important as environmental resistance. You must either use materials closed in the galvanic series or, more commonly, introduce a complete non-conductive barrier.
So what are the necessary mitigation methods for galvanic corrosion? How do you stop this from happening?
Well, the standard practice is isolation. This means using non-conductive washers, such as thick EPDM rubber or plastic, and bushings to physically separate the stainless steel fastener from the less noble metal. Furthermore, sealant materials, if they are non-corrosive and non-acidic, can act as a crucial barrier to prevent the electrolyte, the water, from completing the circuit between the two different metals. Failing to isolate stainless steel from aluminum or copper components in outdoor, wet, or marine environments is an engineering oversight that guarantees premature failure of the assembly.
Okay, so let's transition from the general principles of stainless steel defense to the specifics of our three key grades. We have 304, which is the ISO designation A2, then 316, or A4, and 410, which is C1. Here's where the internal structure, the metallurgy, dictates the entire performance profile of the screw.
And the differences start at the atomic level, specifically in the way the atoms are arranged in their crystal structures. The vast majority of stainless steel fasteners fall into two distinct metallurgical families based on this arrangement: austenitic and martensitic steels. Understanding these two structures is absolutely key to understanding the trade-offs in strength versus corrosion resistance.
Let's start with the most common family for fasteners, the austenitic grades. So that's 304 and 316. What defines their structure, this famous face-centered cubic structure, or FCC?
Austenitic grades are the backbone of the stainless fastener world, really. Their structure is stabilized by the large addition of nickel, or neak, which holds the face-centered cubic, or FCC, crystal structure. You can think of it like stacking tennis balls in a box. It maintains that structure at all temperatures down to absolute zero. This structure gives them superb ductility, toughness, and their characteristic non-magnetic properties. Though cold working can sometimes introduce a little bit of magnetism.
And critically, how do they get their strength? Because this is a huge point of difference.
It is. Crucially, they cannot be hardened by traditional heat treatment methods. You cannot just quench and temper a 304 screw. Their strength, which can range up to property classes like A280 or A4100, is achieved entirely through work hardening, which is the tremendous force of cold deformation applied during the wire drawing and screw manufacturing process. This process distorts the crystal lattice, making the metal harder and stronger.
Now let's pivot to 410, the martensitic grade C1. It operates in a completely different metallurgical landscape.
Completely different. Grade 410 belongs to the martensitic family. Unlike austenitic steel, 410 contains minimal nickel, less than 0.75%, but it contains higher carbon content. This composition allows it to achieve high strength and hardness through the traditional heat treatment process involving quenching and tempering. When it's fully hardened, its crystal structure transforms into a body-centered tetragonal or BCP structure. We can think of that, less elegantly maybe, as a twisted stack of tiny bricks.
And this BCT structure is inherently hard and also magnetic.
It's intensely hard and strongly magnetic. The ability to undergo this heat-induced transformation means 410 can achieve significantly higher mechanical properties than austenitic grades, which makes it ideal for applications that require extreme surface hardness, like the self-drilling fastener we mentioned earlier.
It really seems like nickel content is the fundamental differentiator. It dictates the crystal structure, which then dictates the hardening method and ultimately the performance. Let's look closely at the chemical makeup of these three grades, as the alloying elements are the DNA of performance.
Absolutely. The percentages of the three key elements, chromium, nickel, and molybdenum, write the destiny of the fastener.
Let's start with chromium, the primary corrosion fighter and the defining element of stainless steel.
Okay, so grade 304 contains 18 to 20% chromium. Grade 316 is slightly lower, with 16 to 18% iron. The martensitic grade 410 contains the lowest amount, only between 11.5 and 13.5% iron. The lower chromium in 410 immediately signals its lower baseline corrosion resistance compared to the other two.
Next up, nickel, Ni. The structure stabilizer, the ductility enhancer, and the element most responsible for price volatility.
Nickel is critical for stabilizing that austenitic FCC structure. Grade 304 contains 8 to 10.5% Ni. Grade 316 is even richer, ranging from 10 to 14% Ni. Contrast this sharply with grade 410, which contains less than 0.75% nickel. This low nickel is what compromises 410's corrosion resistance, but paradoxically allows it to be heat-treated for its superior mechanical performance.
Finally, the star of the show for corrosion resistance in aggressive environments, molybdenum or Mo.
Molybdenum is the crucial ingredient that separates the good 304 from the great, which is 316. Grades 304 and 410 have essentially zero molybdenum. Grade 316, however, includes a substantial 2 to 3% molybdenum. This is the marine factor. This molybdenum addition dramatically increases 316's resistance to the two most insidious types of localized corrosion, pitting corrosion and crevice corrosion, particularly when chlorides are present.
We need to spend a moment clarifying those two failure modes because they are silent killers of fasteners. Let's start with pitting corrosion. What exactly is that?
Pitting corrosion is a highly localized attack. It usually begins when the passive film is damaged or cannot self-repair in a microscopic spot. This allows corrosive ions, especially chloride ions, to attack the underlying metal. Instead of rusting broadly across the surface, the corrosion eats downward, creating a tiny, deep hole or pit. This pit then acts as a stress concentration point, weakening the metal far out of proportion to the material loss.
And crevice corrosion, that seems to relate directly to how the screw is installed.
It does. Crevice corrosion happens when the fastener is installed tightly, creating a narrow millimeter-scale gap, a crevice between the screw head or washer and the surface it's clamping down on. This narrow gap is problematic because it traps moisture and chloride salts, and critically, it starves the area of oxygen.
So if there's no oxygen in that tight, salty gap, the self-healing passive film cannot reform itself.
Exactly. The local chemical conditions inside that tight, oxygen-starved, chloride-heavy crevice change drastically. The trapped water becomes increasingly acidic, and the corrosion rate skyrockets. It's a localized, acidic microtrap where the stainless steel's primary defense mechanism, oxygen-fed self-healing, is disabled.
That sounds like a guaranteed failure mechanism in coastal environments. So what does molybdenum do specifically to combat these conditions in grade 316?
Molybdenum essentially stabilizes the passive film against the direct corrosive action of the chloride ions. It achieves this by being incorporated directly into the chromium oxide film, making the film more tenacious and resistant to breakdown, even under those highly acidic, low-oxygen conditions found inside a crevice. This is why 316 is the marine grade, because it provides a reliable long-term defense against the relentless attack of salt spray, de-icing salts, and chlorine-based chemicals. It's a necessary and, yes, expensive insurance policy for high chloride environments. So now we connect chemistry directly to the tangible engineering performance. The decision to use one grade over another is always a calculated trade-off. We are balancing maximum corrosion resistance against the necessary mechanical strength and, of course, the constraints of the budget.
Let's start with grade 304, or A2. Given its 18% chromium and 8% nickel, it sits right in the middle ground. That makes it the industry workhorse, right? So where is its sweet spot?
Grade 304 is the generalist and the cost leader among the high-resistance grades. It offers excellent general corrosion resistance, superb ductility, and great formability. It is the ideal fastener for general indoor and outdoor construction that is far removed from the coast, for food processing equipment, HVAC systems, and dry, controlled interior environments. Its resistance is perfectly adequate for standard rainwater and atmospheric moisture.
But its limitation is sharp and critical: chlorides.
Yes, if you put a 304 screw into an environment rated as C4, which is high corrosivity, or C5, very high corrosivity under ISO standards, which includes areas directly exposed to heavy salt spray or frequent use of de-icing salts on roadways, its service life will be severely compromised. It will typically fail within just a few years due to pitting corrosion. That's the line where 304 stops being acceptable.
Which brings us to grade 316, A4, the premium defender.
Grade 316 is the non-negotiable choice for aggressive environments. Its inclusion of molybdenum elevates its chloride and acid resistance to the necessary level for marine structures, chemical and pharmaceutical processing, where it resists various acids and solvents, and wastewater treatment plants. If a design life of 50 years or more is required in an aggressive outdoor or coastal location, the initial cost premium of 316 is instantly justified by the avoidance of premature failure. It is the gold standard for long-term survival in harsh chemistry.
Finally, grade 410, or C1. It clearly loses the corrosion resistance battle, given its minimal nickel and lower chromium. What specifically does it gain in exchange for that sacrifice?
Grade 410 gains immense mechanical performance and specialized utility. Because it has the lowest alloying content, its baseline corrosion resistance is moderate, far better than plain carbon steel, but significantly worse than 304 and 316. Its strength, however, is exceptional because of its ability to be heat-treated.
And this high strength is essential for its primary application, correct?
Absolutely. 410 is the dominant material for self-drilling fasteners, commonly known as tech screws. For a screw to be able to cut its own hole, tap its own threads, and fasten the material in one single operation, the drill point must be significantly harder than the steel it is penetrating. The 410 grade achieves this by being quenched and tempered to a very high level of hardness, often exceeding 50 HRC, that's the Rockwell C scale, at the tip. And its minimum tensile strengths, the maximum pull force it can withstand, are far beyond the capabilities of non-heat-treated austenitic grades. Let's put those strength standards into context for the listener. When we talk about mechanical properties, we are talking about what the screw can physically bear before it fails. That's right. For the austenitic grades 304 and 316, their strength comes from work hardening. They're commonly specified as property class 70, which is 700 MPa minimum tensile strength, or class 80, which is 800 MPa. To give you a layperson's analogy for class 80, if you took a cross-section of that screw with an area of 1 square centimeter, it could theoretically hold a weight of about 80 metric tons before snapping. That's incredibly strong.
Okay, now compare that to the heat-treated martensitic 410.
The 410 grades, post-quenching and tempering, are often specified in categories equivalent to class 110 or even higher. Not only do they achieve a high tensile strength in the body of the screw, but their surface hardness must be extreme for drilling. That 50 HRC figure we mentioned, that high hardness is achieved by transforming the microstructure into martensite, which is intrinsically brittle if handled improperly.
That high hardness, while necessary for drilling, brings us back to a failure mode we touched on earlier, a really dangerous one. We're talking about delayed catastrophic failure.
We are. This is the critical trade-off of using high-strength martensitic steel. Any steel hardened to such a high degree, typically above 40 HRC, becomes highly susceptible to a failure mode called hydrogen embrittlement, or HE.
How does hydrogen get into the screw in the first place, and why does it matter so much?
Well, hydrogen embrittlement occurs when atomic hydrogen, a byproduct of processes like acid cleaning, pickling, or, most commonly, electroplating like zinc or cadmium plating, is absorbed into the metal structure. In a high-strength, hard, crystalline structure like fully hardened 410 martensite, these tiny hydrogen atoms diffuse to points of high internal stress, and they essentially weaken the bonds between the steel grains.
So the fastener is installed, and it's under high tensile load, but the failure doesn't happen instantly.
No, it is insidious. The failure often occurs hours or even days after installation, and potentially under only 10% to 20% of its normal rated load, because the absorbed hydrogen finally concentrates enough to cause a brittle sudden fracture. For standard carbon steel bolts, the solution is a required immediate post-plating baking process to drive the hydrogen out.
So given that 410 screws are already high strength, the manufacturing process for cleaning and hardening them must be absolutely flawless, because the margin for error against hydrogen embrittlement is tiny.
The margin is tiny, and the risk is real. While 410 stainless steel is often treated to mitigate internal stresses, its core susceptibility to HE remains a major concern if it is subjected to any hydrogen-generating processes post-hardening. This is why specifiers must understand that when you choose 410 for its speed and strength, you're accepting both lower general corrosion resistance and a higher risk profile regarding delayed brittle fracture compared to the more ductile, less susceptible austenitic grades, 304 and 316.
Okay, so to summarize this part, 304 is the generalist for benign environments. 316 is the marine specialist and chemical defender, and 410 is the structural speed demon, trading corrosion defense and hydrogen embrittlement risk for drilling capability and supreme mechanical strength. This brings us neatly to the final and often decisive factor, the cost. If 316 is the most robust, why isn't it the standard choice for everything? The answer lies in the economic equation, balancing the initial purchase price against the long-term reality of the total cost of ownership, or TCO.
The price of stainless steel is remarkably elastic. It's dictated heavily by the volatile global cost of the core alloying elements, primarily nickel and molybdenum. Because these are expensive commodities, there is a very clear and unavoidable price hierarchy.
Let's nail down that hierarchy for everyone.
Starting with grade 410. Because it uses minimal nickel and no molybdenum, it sits at the bottom of our scale. We can set a base price index of 1.0x. This is the cheapest stainless option. Moving up, grade 304 requires significant nickel content, pushing its cost up, typically indexing around 1.8x the price of 410.
Wow, almost double the price just for the nickel and slightly higher chromium content.
Correct. And then we have grade 316. This is the premium option. It includes both high nickel plus the expensive molybdenum. It typically commands a price index of roughly 2.5x the cost of 410. When you are buying hundreds of thousands of fasteners, that 150% increase between 400 and 316 is a massive capital expenditure decision.
So, if a project requires 10,000 fasteners, the purchasing department is under immense pressure to pick the lowest initial price. They're often pushed toward 304 or even 410. Why is focusing purely on the initial unit price insufficient for sound engineering?
Because the initial purchase cost is only the tip of the iceberg. An engineer must adopt a total cost of ownership TCO mindset, which looks at the cost over the entire intended lifespan of the structure. That could be 20, 50, or even 100 years. We have 4 crucial cost elements here, and 3 of them happen after the purchase.
Okay, let's elaborate on those post-purchase costs. Start with installation cost.
Installation cost is primarily labor. This is where the structural speed demon, the 410 self-drilling screw, offers its greatest economic advantage. By consolidating the process of drilling a tiled hole, tapping the threads, and seating the fastener into one rapid action, 410 can dramatically reduce installation time. If labor costs, say, $50 per hour, and you are installing thousands of screws on a massive cladding project, saving even 30 seconds per fastener can translate into massive savings. Savings that can easily absorb the slight price difference between a 410 stainless and a cheap galvanized alternative.
So speed and efficiency are a legitimate factor in the TCO calculation, justifying the material choice. What about the biggest financial risk, maintenance and replacement?
This is where underspecification becomes devastating. Let's say a contractor decides to use grade 304 screws in a location that is, unbeknownst to them, designated C3 medium corrosivity. Maybe it's near an industrial park where airborne sulfates or chlorides are present. The 304 fasteners will begin to fail prematurely, perhaps 5 to 8 years into a 25-year design life.
And the cost to fix that failure is exponential, isn't it?
Absolutely. The cost of the replacement screw itself, say 25 cents for a 316 replacement, is insignificant. The true cost is the labor required to access the failed connection, often requiring scaffolding, removing structural panels or cladding, replacing the fastener, fixing any localized damage caused by the rust bleeding, and reassembling the whole structure. That can easily cost $50 to $100 per failed fastener, dwarfing the initial investment.
And the most catastrophic element is the cost of failure. This moves beyond simple maintenance and into liability.
The cost of failure covers everything from aesthetic damage to outright structural collapse. We have all seen examples of new architectural facades marred by red-brown streaks. That rust bleeding is a visual manifestation of pure financial failure. It ruins the aesthetic intent of the design, leading to costly remediation or even major litigation. For load-bearing structural connections, a complete brittle fracture due to hydrogen embrittlement in a high-strength fastener, or a massive loss of cross-section due to crevice corrosion, is a public safety hazard. The resulting legal liability, cleanup costs, and reputational damage can be orders of magnitude greater than any money saved by skimping on 316 initially. So the ultimate cost effectiveness is found not in the cheapest option, but in the option that provides the necessary longevity for the environment. How do engineers use the corrosion classification system to make that exact decision? They rely on international standards that classify the atmospheric corrosivity of the installation environment. These typically range from C1, which is very low corrosivity, like a controlled interior office, up to C5, which is very high corrosivity, like an industrial area near the coast.
So it's a simple matching game.
It is. If the site is C3 or lower, passivated 304 is usually the most cost-effective solution, balancing excellent resistance with manageable material costs. If the site is C4 or C5, meaning heavy industrial pollution, high humidity, or coastal exposure, then 316 is no longer a luxury. It becomes a mandate to meet the design life. Underspecifying is a technical and financial guarantee of early failure. Conversely, using 316 in a C1 environment where 304 would last 100 years is financially wasteful, albeit technically safe.
That is a perfect framework. It transforms the conversation from just buying a commodity item to making a critical, calculated engineering decision defined by 3 variables: material alloy, strength class, and corrosion grade.
To synthesize our deep dive, we have firmly established that stainless steel's remarkable longevity and self-repairing capability stem from that invisible, passive, self-healing chromium oxide layer. The 3 grades we analyzed offer distinct design pathways tailored for specific needs.
We've learned that grade 410, the martensitic C1 grade, prioritizes high strength and drilling ability. It achieves its properties through heat treatment, a process that must be meticulously controlled to avoid the delayed risk of hydrogen embrittlement. Grade 304, the austenitic A2 grade, is the cost-effective workhorse for general non-chloride heavy environments, achieving its strength through cold work.
And grade 316, the premium austenitic A4 grade, is the ultimate defender. Its crucial addition of molybdenum provides a highly stable passive film, offering superior defense against the highly localized and insidious attacks of pitting and crevice corrosion, making it indispensable for marine and chemically aggressive applications.
The key takeaway for you, the listener, is that when selecting any fastener, you are making an engineering risk assessment. You must audit your environmental specification and match the alloy to the anticipated corrosivity. Adherence to standards like ISO 3506, which defines these A2, A4, and C1 grades, is the bedrock of predictable, reliable, and cost-effective construction.
And we have seen that the hardening methods are profoundly different. Ductile austenitic steels rely on cold work. Strong martensitic steels rely on quenching and tempering. This distinction is vital when assessing long-term structural integrity and delayed failure risks.
And that leads us back to our final provocative thought for you, building on our earlier discussion of the 410 trade-off. We know that any electroplated high-strength fastener is highly susceptible to hydrogen embrittlement.
And given that the high strength of martensitic 410 stainless steel is achieved by pushing the material into that hard, high HRC brittle range through heat treatment, and knowing that manufacturers strive for flawless processes.
Why? The question remains. When sourcing high-strength 410 screws, how much faith must a specifier place in the supplier's quality control to ensure that zero hydrogen was introduced during acid cleaning or any post-treatment? Is the calculated risk of using a super-hardened but potentially vulnerable 410 grade with its inherent susceptibility to delayed brittle fracture under load truly worth the installation efficiency it provides, especially when lives or huge financial liability are at stake?
It forces us to ask whether the cost saving in installation labor is sufficient compensation for accepting a manufacturing risk that could lead to catastrophic failure years after the job is finished. That is a question of risk management that every professional must grapple with when dealing with high-performance fasteners.
Indeed. We've gone from the macro view of a structure down to the atomic interactions that prevent rust. Thank you for joining us on the deep dive.
We'll catch you next time.